So thank you, and again, welcome to your Friday Happy Math Hour. Just like Mr. Sazi, I'm going to be taking over for him today. So I'll be sharing my screen. So please, I can see if you guys have your hands raised or something. So if you have a question, please feel free to unmute your mic and let me know. Okay. If I need to go slower or go over something again, please feel free to ask any questions. So let's go ahead and get started. So for today's Happy Math Hour session, we are going to be looking at basic matrix operations and its inverse. Okay, so what do we mean by the basic matrix operations? So we're going to be doing addition of matrices, subtractions, multiplication, and then we'll do some application problems, which are some real life examples and also reviewing what it means to have the size of the matrix, okay? And then when we deal with the product and inverse of matrices, again, which we're going to show you how to do matrix multiplications, what is an identity matrix, and how to find an inverse matrix, and what is an inverse matrix, okay? So first, let's start with what is a matrix and or why are matrices useful. So matrices are used practically much anywhere. Um, and if I let you in a little bit into my field, I started under engineering, and we use matrices a lot for for coding and for security purposes. So matrices are it's a wonderful tool to have and to be able to use. Okay, so and the reason why they're so great is because it's a great way to organize data, and it has it in order. And again, that's why we would use it a lot in programming, because it has an order where it's fixed, and we can use that for a lot of applications that you see here: management, natural science, social science, and again, engineering is used tremendously a lot, and that's what I'm familiar with. Um, so let's start to get you to hopefully like matrices. We have a first example here, and it deals with like a real world application. We have a furniture manufacturing company, and here we call it the Easy Life company, manufactures sofas and armchairs, and they have three models, and we're just for simplicity purposes, we're just going to call them A, B, and C. Okay, so the company has regional warehouses in New York, Chicago, and San Francisco. And it turns out that in August, the shipments that the companies would send out were 10 model sofas of A, 12 model sofas of B, 5 model sofas of C, 15 models of A chairs, 20 models for company B of chairs, and 8 model C chairs, and these are for each warehouse, respectively. So our question is, this can this data be organized in any way? And the answer is yes. We can use this information to organize it, and the best way to organize this is to use a matrix. Okay, so we have this data. We have our sofas that are made by each model A, B, and C, which is our manufacturing companies, right? And for instance, for the sofas, model A had 10, model B had 12, model C had 5. Um, then we also have chairs. The model A had 15 shipped out in August, model B had 20 shipped out in August, and model C had 8 shipped out in August. Okay? All right, so to alternatively, we might tabulate the data. What we can do is we can create something like this. This would be um, our our table, and that's what's called a tabulated data, right? So we can create a table where we have our furniture. Here's the sofas and chairs, and then these are the models based on the company, right? A, B, and C. And again, these are their quantities. All right, so if you see here, what I can do is get this table that I just created and create a matrix from it. So first, and I'm going to go into detail how we label matrices, but here in this particular example, straight off the bat, I'm going to call this matrix M. So matrix M has this first row, the atoms for the sofas, which are 10, 12, and 5. And then I have a second row that deal with the numbers of the chairs, the 15, 20, and 8. And the last thing that I'm going to do is I'm going to encapsulate these values by brackets. So believe it or not, what I just created here is a matrix based on this information. And again, the reason why we can use matrices is because they're going to have this order that we know based on my table here, that in the first row, we're talking about the sofas. In the second row, we're talking about the chairs. And the column 1 has to deal with the model A, column 2 with model B, and column C with um, um, column 3 with model C. So again, this refers to, again, our rows for furniture, sofas, and chairs. Okay, and again, this is what I explained. The columns refer to our models. All right, so let's go into um, a more general term of what a matrix is. Okay, so when we are using matrices, when we label them, we can label them whatever we want. We want to be able to distinguish one matrix from the other, so we give them names. Okay, so and we set them equal to the name. So in convention, especially for our class, most of our matrices we're just going to call them A, B, or C, and we're going to use capital letters for the names. Okay, um, so for the elements inside the all the values that we're going to put inside our matrix are called the elements of the matrix. And for the elements of the matrix, we're going to use lowercase based on the name of the matrix. So for instance, an example, that first one here, we have matrix A. So all the elements have a lowercase a here. Now let me explain a little bit um, these numbers that you see here. Each element here in the matrix has a specific address. As I was telling you, matrices are great to keep order. So each element in the matrix has a special order, or I would like to say is an address. So for instance, in my matrix A, the first um, element here, A11, and the 1 is like a subscript. What this is saying is that this element belongs in row 1, column 1. Then the second one here, A12, what this is referring to is the element in row 1, column 2, and so on and so forth. Okay, so let's give you an example here, as when we are reading the matrices is always row and columns. Okay, so again, row 1, column 1, row 3, column 2. Again, this is what the subscripts mean. They're the addresses of the matrices. Okay? So the position of the element, um, A11, again, refers to the row 1, column 1 position. Okay, and again, these are just examples. A14, again, what would this mean? Because you have homework problems that are going to tell you this. What is the position of A14? So A14, you would go to the position in row 1, column 4. A23, you're going to go to row 2, column 3. Yes? So this is how we read elements in our matrix. They're based on the row and then the column. So for instance, if I had this matrix now with number examples, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what is the position of the following elements? A13. So for A13, the 1 refers to my row. Okay, so it's row 1, and the 3 is the column 3. So the number in or the element in A13, the answer would be 3, right? Okay. So what about A24? This one is saying A24, so it's row 2, column 4. So in row 2, and I go to column 4, the value here is 8. So this is how we find positions of elements in our matrix. Now let's look into determining the size of the matrix. So as I was explaining to you, when we're reading elements in the matrix, it's always first the row and then the column and the numbers. But this is the definition of the size of the matrix. The size of a matrix is the number of rows by the number of columns. And we use the X symbol for the by, the multiplication symbol. Okay, so number of rows times the number of columns, and this is the syntax for doing the dimension or the size of the matrix. So here for this example that we had just done here, we saw that we had 2 rows and 4 columns. So the size of that matrix is a 2 by 4 matrix. 2 rows, 4 columns. Okay. All right, so example, determine the dimensions of the matrix. So we have 3 matrices here, and we need to find its dimensions. Again, what do they mean dimensions? Their size. So let's look at this first one. So this first one here, we have 1, 2, 3 rows, and then we have 1, 2, 3 columns. So the dimensions of that first matrix is a 3 by 3 matrix. Okay, let's look at the second one. Okay, we have 1, 2, 3 rows and only 1 column. So the dimensions of the matrix is a 3 by 1. Okay, and then the last one, this matrix, which is just 1 row, but we have 1, 2, 3 columns. So the size of this matrix or the dimensions of this matrix is a 1 by 3 matrix. Okay, so it's very crucial to know the size of the matrix because we're going to need this information later on. Okay, so we need to know what the size of the matrix is. Okay, so let's look at this one. Determine the order of the matrix. So what is the order of the matrix? So the order of the matrix, again, this is a 4, 1, 2, 3, 4 rows and 2 columns. So whenever they ask you the order of the matrix, what they're also asking you is the dimensions or the size. Okay. All right. So now that we have some information on matrices, let's go ahead and practice doing matrix operations. And again, matrix operations that we're going to go over is adding, subtracting, multiplying, and dividing matrices together. Okay, so let's give first a general explanation of the matrices. So again, let's say that I have these 2 matrices, A and B. So in order for us to add or subtract matrices together, they must be of the same size. So it's just what we covered. For us to be able to add or subtract 2 matrices together, they need to have the same dimension, or again, the same size. If they're not the same dimensions, then we cannot add them. And you can think of it as like adding and subtracting like terms. For us to add or subtract terms, they have to be like terms. For instance, if I can add 2x with 3x because they have the like terms, they both are x terms. So 3x plus 2x would be 5x, but I cannot add 3x plus 5y. X and y are different terms. They cannot be added to each other. Same thing with matrices. If they're not the same size, then they're not like the same term, so I cannot add them together. So let's do an example. So I want to add matrix A with matrix B. So let's say that again, this is in general, and matrix A and matrix B are the same size, then what you're going to do is just as it says here, you're going to add the address with the first with the same address of the second. For example, on matrix A, the address A11, that element refers to row 1, column 1. Well, that element is going to be added to the same address of the second matrix. So matrix B, I'm going to add it to the element that is in row 1, column 1. And you're going to do that for all of the elements. Okay? So you go down and each address matches the address of the other. And that's how you're going to do this. This is matrix addition. So the sum of 2 matrices, again, all you're going to have to do is summing up the corresponding elements of both matrices. In this case, the x and y of the matrices were called the x and y. Okay, so Similarly, subtraction works the same way. For us to do subtraction, we have to be dealing with the same size of the matrices or the same dimensions. And the way you're going to do the subtraction is you're going to subtract um, each element that corresponds to the address of one with the other. Okay, so the best way to see this, and you're going to see this is very easy, is with an example. So let's go and see this example. Let's say that I have these three matrices, A, B, C, and D. Okay, they're all capital letters, so these are my names. So let's go through the sizes of the matrices. Okay, so the first matrix is a 2 by 3 matrix. The second is also a 2 by 3 matrix. The third one is a 2 by 2 matrix, and the last one is a 2 by 2 matrix. Okay. All right. So I want to add matrix A with matrix B, and the first thing you got to ask to yourself is the size of matrix A the same as size of matrix B? And the answer is yes, right? Both of them are a 2 by 3 matrix. The size is the same, so then that means that I can add them together. So what I'm going to do is I'm going to get the element in row 1, column 1 of matrix A, which is 1, and I'm going to add it with the element of the second matrix B, the row 1, column 1, which in this case is 8. And I'm going to do that for each of the elements. So minus 3 plus 0, 2 plus 1, 2 plus a negative 1, 2 plus 3, and negative 1 plus 4. And again, as you can see, versus this last one, the negative 1 here is in row 2, column 3, and it's going to be added to the row 2, column 3 of B, which is the 4. So then I'll just do the operations. So here, 1 plus 8 is 9, minus 3 plus 0 is negative 3, 2 plus 1 is 3, 2 plus a negative 1 is 1, 2 plus 3 is 5, and negative 1 plus 4 is 3. Okay, so the addition of matrix A and B is this answer: 9, negative 3, 3, 1, 5, 3. And if you see, we're going to get the same size of the matrix. The dimension, the result should be the same as the addition to the 2 by 3 matrix. Okay, so let's try C and D. Can I do C and D? The answer would be yes, because the size of matrix C is a 2 by 2 matrix. The size of matrix D is also a 2 by 2 matrix. So then that means I can add these two matrices together by adding the address that corresponds to the other address. Okay, so again, 5 with the 2, the 1 with the negative 1, the negative 4 plus the 9, the 3 plus the negative 7. Okay, so let's simplify our work. So again, don't forget when we have to use the brackets. Give me 1 second. Let me connect my laptop. Okay, there we go. Um, so let's do. Oh, I was mentioning that don't forget to write the brackets. The brackets mean that we are dealing with a matrix. Okay, so it's very important that you don't forget the brackets. So I wrote my brackets. So now I'm ready to find my final answer for my matrix. So 5 plus 2 is 7. 1 plus a negative 1 is 0. Negative 4 plus 9 is 5. 3 plus a negative 7 is a negative 4. And that's the addition of matrix C and D. Okay. All right. So what about if I wanted to sum matrix A with matrix C? And if I see matrix A is a 2 by 3 matrix, C is a 2 by 2 matrix, these are two different sizes. So the answer that you would put on your homework would be not possible. You cannot add them together because they're not the same size. Okay? So what if we want to do the subtraction? Let's practice subtraction, which is very similar, hopefully just as easy. So again, these are the sizes of our matrix, just so we don't forget. So let's go ahead and do now A minus B. And to do A minus B, or subtract matrix A with matrix B, it's the same process. We're going to subtract the corresponding address of the first with the corresponding address of the second. So here, we know we can add them because they're the same size, but now I'm going to do subtractions. 1 minus 8, minus 3 minus 0, 2 minus 1, 2 minus a negative 1, 2 minus 3, negative 1 minus 4. Let's go ahead and simplify our answer. So 1 minus 8 is a negative 7. Negative 3 minus 0 is a negative 3. 2 minus 1 is 1. 2 minus 1 is 3. 2 minus 3 is a negative 1. A negative 1 with a negative 4 is a negative 5. Yes? So let's just practice the last one that I can do. C minus D. I can add these two because I know that they're the same size. They're a 2 by 2 matrix. So here, again, it's going to be 5 minus 2, 1 minus a negative 1, negative 4 minus 9, 3 minus a negative 7. Let's go ahead and simplify. 5 minus 2 is 3. 1 minus a minus 1 is a 2. Negative 4 minus 9 is a negative 13. 3 minus a minus 7 is 10. Yes? Um, and again, if they had asked me to do subtract A minus C, I know that A is a 2 by 3 matrix, C is a 2 by 2 matrix. They are not of the same size or dimension, so I cannot add them. So the answer would be possible. They're not the same size. Okay? All right. Again, if you have any questions, please unmute yourselves. Be confident. Don't be shy. If I'm going too fast, please stop me. Let me know if you need me to go over anything. Okay. All right. So the first multiplication that we want to practice is something called scalar multiplication. This is the most simplistic scalar multiplication, and what this means is that we're not going to multiply to we're going to be given a matrix, but we're only going to multiply a value to a matrix or a scalar value, in this case k, as your book describes as far as the definition. So as an example, let's say that I have this matrix X, and it's a 2 by 3 matrix, and these are the elements 2, 0, 5, 4, negative 2, negative 3. And I want to find 6x. So if you see here, I'm not multiplying anything other than a scalar value, a number, a 6 to this matrix X. So the way to do this is that the 6 is going to be multiplied to each element in the address of the matrix. So let's go ahead and do this. So this 6, I'm going to multiply this to this matrix, which is 2, 0, 5, 4, negative 2, negative 3. And what this means is that 6 is going to be multiplied to the 2, it's going to multiply to the 0, it's going to multiply to the 5, it's going to multiply to the 4, it's going to multiply to the negative 2, and it's going to multiply to the negative 3. Then I just simplify. 6 times 2 is 12, 6 times 0 is 0, 6 times 5 is 30, 6 times 4 is 24, 6 times a negative 2 is negative 12, 6 times a negative 3 is a negative 18. Okay? So this is what's called scalar multiplication, when I'm just multiplying a number to a matrix. And to do that, I just multiply that number to each element in the matrix. Okay? All right, what if I want to find negative x? Okay, so what that is saying is I want to multiply a negative 1 to matrix x, right? So that's what that means. Okay, so I'm going to multiply a negative 1 to my matrix x, which is again 2, 0, 5, 4, negative 2, negative 3. But this is also a scalar multiplication. I'm multiplying that negative 1 to each element in that matrix. So let's go ahead and do that. So that means that I'm going to multiply 2 times a negative 1 is a negative 2. Negative 1 times 0 is 0. Negative 1 times 5 is a negative 5. Negative 1 times a positive 4 is a negative 4. Negative 1 times a negative 2 is a positive 2. And the negative 1 times a negative 3 is a positive 3. Okay? All right. So these were examples of scalar multiplications. Okay? Now let's look at building up to a more complicated problem where we have to apply scalar multiplications with the addition. Okay, so for instance, let's and even though these are 3 questions on your homework, it's probably going to be 1. It's going to say find minus 4a plus 5b. And the best way to do it is always let's do it in pieces. Okay, so let's say that we have matrix A, B, this by 2 matrix, a negative 2, 0, 5, 3. Let's have matrix B, be also a 2 by 2 matrix, and it's 0, 2, 4, -6. So the first thing that I want to do, again, just to follow the numbering here, but it's building up to question 3, is first I'm going to find what -4a is. Okay, so that is a scalar multiplication of matrix A. I'm going to multiply -4 to matrix A. So again, I'm going to multiply -4 to matrix A, which is -2, 0, 5, 3. Again, this -4 has to be multiplied to each element in the matrix. So let's go ahead and do that. -4 times a -2, -4 times 0, -4 times a 5, -4 times a 3. We simplify, we have positive 8, 0, -20, -18. Yes? No, excuse me, -12. So that one was the first one, -4a. So the next thing that they're asking me, or I want to do, is do 5b. Again, this is another scalar multiplication of 5 times b. So I'm multiplying 5 to matrix b, which is 0, 2, 4, -6. Let's go ahead and do this. So we have 5 times 0, 5 times 2, 5 times 4, 5 times a -6, which is going to result in 5 times 0 is 0, 5 times 2 is 10, 5 times 4 is 20, 5 times -6 is a -30. Yes? All right, so I did the second. Now they're asking me to do 3. I want to do -4a5 plus 5b. But since I already did that work, I can just put it together, right? So -4a is that matrix in blue, which is 8, -20, 0, -12. And I'm going to add it to matrix of 5b, which is the one in red, which is the 0, 10, 20, -30. So now again, this is just an addition of two matrices that we know how to do, is adding element with element, right? So here we want to do 8 plus 0, 0 plus 10, -20 plus 20, -12 plus a -30. Let's simplify. 8 plus 0 is 8, 0 plus 10 is 10, -20 plus 20 is 0, -12 minus 30 is a -42. Okay, so these were basic fundamental operations with matrices, but let's do something a little bit harder. And let's revisit our first example of a real world application, the furniture manufacturing company, the Easy Life company. So let's say that we have this matrix, right? That C stands for Chicago, and just to play with the words, right, to make it truly real world. So we have this manufacturing company C for Chicago, and these are the numbers for sofas and chairs. So the question says, during August, the Chicago warehouse shipped out the following numbers of the matrices with the given agencies, which we did earlier, right? So, and then we have this now, they're asking us this. What was Chicago's warehouse inventory at the end of September, taking into account only the number of times received and sent out for the month? All right, so let's see here. So here we have C for the Chicago, which is our warehouse of the items we have, and K is the shipments that we had for the month of September. So what we want to do is we want to do C minus K, okay, to find the differences of what had shipped out, right? So again, we can do this. We can subtract these two matrices because they're both the same size. They're both two rows and 3 columns. The sizes match. Okay, so this is C. I'm going to subtract it with K, which K is this one. And again, to do the subtraction, I'm just going to subtract address with address and with each corresponding element. Okay, so let's go ahead and do this. So our answers would be 10 minus 5 is 5, 12 minus 10 is 2, 5 minus 3 is 2, 15 minus 13 is 2, 20 minus 12 is 8, and 8 minus 8 is 0. Okay, so again, we can answer what was the Chicago's inventory? Well, we took out everything that got shipped out. Yes. Okay. Now, Um, we have here in red, very, very, very important. Now what we want to do is we want to deal with multiplication of matrices. But just like there was a condition to add and subtract matrices, in order for us to add and subtract matrices, we had to have the same size of or same dimension of matrices for each one, right? But for matrices is a little different, and you have to meet these conditions. Okay, so if you're given two matrices A and B and you want to multiply them together, you have to do this condition. The columns of the first matrix have to be equal to the rows of the second matrix. You have to meet this condition. If this is not met, then you say it's impossible, cannot multiply these matrices together. So again, in order for us to multiply two matrices together, the columns of the first matrix have to equal the number of rows of the second matrix. Now, another piece of information is that the solution of the matrix of the or the product of the matrix, the size is given by the number of rows of the first matrix with the columns of the second matrix. That's the solution matrix, or that's our answer. That's the size of our matrix when we do the multiplication. So, um, if I ask you, if the size of the matrix A is a 2 by 3, then matrix B must be what? So for us, if we want to multiply matrix A with another matrix, the other matrix has to have um, a, how many rows should it have? Well, the answer would be 3. This has to match. So matrix B has to be 3 times, it doesn't matter. Who cares how many rows, columns it has, as long as it has 3 rows that is matches the columns of the first, we can multiply. Okay, so the solution is going to be a 2 by whatever matrix or whatever number you want to put in there. So let's go ahead and do this example. Given the following matrix, state whether the matrices can be multiplied. Let's just first see, let's and review if we can or cannot multiply matrices together. Then we'll do one that we will multiply. Okay, so first let's start with this. I give you matrix A, which is this. That's a 2 by 3 matrix. And let me give you B. B is a 2 by 2 matrix. Can I multiply these two matrices together? Well, let's see. Again, the best way is to write the sizes down, right? Well, first, let me give you another matrix C for right now, but let's write the sizes. Okay, so again, matrix A is a 2 by 3 matrix, matrix B is a 2 by 2 matrix, matrix C is a 3 by 2 matrix. Okay, all right, so this is the question to you. Can I multiply matrix A and B together? So if we see here, the columns of matrix A are 3, but the rows of matrix B are 2. These do not match. So for this problem, A, since the columns of the first do not match the rows of the second, the answer would be no match, so cannot multiply, or you would say impossible. Okay? How about BA? So B is a 2 by 2 matrix. C is A is a 2 by 3 matrix, but now they match, right? Um, the columns of the first match the rows of the second. So the solution, we can multiply it, and the solution is going to be the the rows of the first with the columns of the second, which is a 2 by 3 matrix. That's our answer going to be. How about this last one, AC? Um, I want to multiply. I want to multiply matrix A, which is a 2 by 3 matrix, with C, which is a 3 by 2 matrix, and we see that the columns of the first match the rows of the second, so it is a match. So yes, we can multiply, and the answer or the product is going to be a 2 by 2 matrix. The columns of the first with the columns of the second. Okay? All right. So now that we know that we can multiply these, let's go ahead and multiply this. Let's multiply B with A. Okay, so again, B is a 2 by 2 matrix, A is a 2 by 3 matrix, and the resulting matrix is going to be a 2 by 3 matrix. Okay, all right. So step one, let's go ahead and write the matrices. So matrix B is 1, 0, 4, negative 2. Matrix A is 2, 0, 5, 4, negative 2, negative 3. Now, what I tell my students to remember how to do matrix multiplication is, how did you find the size of the matrix? To find the size of the matrix is the number of rows times the number of columns. Well, guess what? This is how you're going to multiply matrices. You're going to multiply matrices row times column. What do I mean by that? Let me show you. Okay. So here, I'm going to multiply first. Um, row 1 is, I'm going to multiply 1 times 2. Okay. So if I'm thinking of the address, okay, I'm multiplying this number 1 that is in row 1 with the 2 that's in column, um, I'm sorry, with the column 1 that's in the matrix 2, which is 2, right? So that's address 1 1. That multiplication of 1 times 2 should be in address 1 1, meaning row 1, column 1. Okay, then the next one, I'm going to add it because there's two numbers in this row, right? The second number in the row is 0. So again, it's row times column. I'm going to multiply 0 times the second number in that first column, which is 4. Okay, so it's 0 times 4, row times column. And then I'm going to add them together. So let's go ahead and do all the additions. Let's do the, or actually we'll do the answer. So the first value, the first element here in our element is 1 times 2 is 2, 4 times 0 is 0, so 2 plus 0 is 2. So that's the address 1, 1. Okay, that goes there. So let's do it again. Step 2, um, I'm going to multiply now. Let's see here. I'm going to multiply row 1 with column 2. Okay, row times column. So 1 times 0 plus 0 times a negative 2. And when I do this, again, 1 times 0 is 0, 0 times negative 2 is 0. So if you see, what I did was multiplied row 1 with column 2. What is that address? That address is 1, 2. So that address 1, 2 goes there. Row 1, column 2. That's the answer. Okay, let's try it again. Step 3. Okay, now I'm going to multiply row 1 again with the last column, with column 3. Okay, so I'm going to multiply 1 times 5 plus 0 times a negative 3. So 1 times 5 is 5. 0 times negative 3 is 0. So 5 plus 0 is 5. Again, I multiplied row 1 with column 3. So this number belongs at address 1, 3. Row 1, column 3. That goes right there. All right, so I did all of the multiplications, row times columns, with the first row. So now the next step is to go into the second row now. Now I want to multiply the second row with the first column. So I'm going to multiply 4 times 2 plus negative 2 times 4. So let's do the math. 4 times 2 is 8. Negative 2 times 4 is a negative 8. So 8 plus a negative 8 is 0. So if I say to myself what I multiplied row 2 with column 1. That is the address 2, 1. So that 0 belongs in row 2, column 1. All right, let's do the next step. Okay, I multiplied the second row with the first column. Now let's multiply that second row with the second column. Okay, and they're in red. So here I'm going to multiply 4 times 0 plus negative 2 times a negative 2. 4 times 0 is 0. Negative 2 times a negative 2 is a positive 4. So 0 plus 4 is 4. This address again is row 2, column 2. So that belongs in the row 2, column 2 address of our solution, which is that 4. Okay, let's do the last multiplication. And I'm going to multiply row 2 with column 3. So again, 4 times 5 plus negative 2 times a negative 3. So 4 times 5 is 20. Negative 2 times the negative 3 is a positive 6. So 20 plus 6 is 26. So this product was in row 2, column 3. So that belongs in address of the row 2, column 3. And there we go. I multiplied um, B times A. And if you see, the resulting matrix is a 2 by 3 matrix. Okay, so this is how we do matrix multiplication. Our solution for this is 2050426. Okay, all right. So now let's switch over to what the identity is. And the best way that I like to tell my students what the identity matrix is it's basically the value one for a matrix. Okay, so it's like if we had a matrix that the value was one, well that's what the identity matrix is. Okay, so and here, if you see the identity for any number one that we covered in 1.1, is that when you multiply anything by one, you're going to get back itself, right? So a times one, the answer is just a, right? Um, so this is the same thing that the identity matrix will do to us. That if we multiply um, a matrix A, which is with its identity, um, or vice versa, again, one times any number is the same thing as the number times one, right? The order doesn't matter. So what we're going to get back is the matrix itself. So, for instance, let's find the identity of a square matrix, but maybe I need to also identify what a square matrix is. Okay, a square matrix is a matrix that has the same number of rows and the same number of columns. Okay, that's what a square matrix means. Square matrix is same number of rows with the same number of columns. So here we have these identities: 1 by 1, 2 by 2, 3 by 3. So the identity matrix of a 1 by 1 is just a matrix with the value 1. The 2 by 2, the identity matrix that makes this 1 is 1, 0, 0, 1. For a 3 by 3 matrix, it's 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so these are the identity matrices for these square matrices. Again, for a 1 by 1, 2 by 2, 3 by 3. These are like my equivalents of 1. Okay. All right. So an example. Let's say that I give you matrix A, which is A, B, C, D. Okay. Identify its inverse or its identity. Excuse me. So the identity of this matrix, okay, is a 2 by 2 matrix. So the identity of this matrix is it doesn't matter what the numbers are here for A, B, C, and D. Its identity is just going to be 1, 0, 0, 1. It's the 2 by 2 identity because the matrix was a 2 by 2 matrix. Okay? Um, Now find A times its identity. Okay, so let's practice. We're gonna practice multiplication so you can prove to you that it's just like one. We're gonna get back the matrix itself. So if I have matrix A, which is A, B, C, D, and I multiply it times what I'm saying, it's an identity, 1, 0, 0, 1, which is just one. I should get the answer back. The answer when I multiply these two together, I should get back A, B, C, D matrix. Okay, so let's go ahead and do this. We're gonna do row times column. So A times 1 plus B times 0 is going to give me A. So that goes in the row 1, column 1. Let's do it again. Let's do row 1, column 2. Okay, so we have A times 0 plus B times 1. A times 0 is 0, B times 1 is B. So that's address 1, 2. That's row 1, column 2. So that goes there. Okay, now let's do step 3. Now let's do the row 2 with a column 1. That's address 1, 2. 1, 1, excuse me, row 1, column 1. So C times 1 plus D times 0. So C times 1 is C. D times 0 is 0. C plus 0 is C. That goes there. And then the last multiplication, row 2, column 2, address 2, 2, multiplied with my identity, um, which is the second row, 0, 1. So we have C times 0 plus D times 1. So C times 0 is 0, D times 1 is D, 0 plus D is D, and that goes there. And voila. When I multiplied matrix A with its identity, I got back the matrix, which is A, B, C, D. Okay, so that's what an identity matrix is. It's a formal way to write a matrix that the value is one. Okay, now um, now what we want to do is we want to look at an inverse matrix. Okay, this is our last topic. Recall that for every non-zero value A, we have an inverse. Okay, so hopefully we all know what an inverse is. It's like the opposite, right? Um, so if we were to multiply A with its opposite, and the syntax for an inverse matrix, we write an exponent of -1. This means inverse. So whenever you're having to find the inverse, the name that you're going to give it is with the exponent of -1. Whatever name you gave that matrix, its inverse is that syntax. So when I multiply a matrix with its inverse, what I'm going to get back is the identity of that matrix. I'm going to get one. Okay, so this is what an inverse matrix is. So let's look at these two matrices. I have matrix A, which is 1, 2, 4, 6, and I have matrix B, which is -3, 1, 2, and 1 half. And the question says, given these two matrices, determine whether matrix B is an inverse of A. So the way I'm going to determine this is that if I multiply these two matrices together, and my answer is the identity, and these are square matrices, these are 2 by 2. So that means if my answer is 1, 0, 0, 1, then they are inverses of each other. So let's go ahead and do that. Let's go ahead and this is the solution that I better get when I do the multiplication. So, um, and I guess I didn't do it. Um, so if I were to multiply this, I'm gonna see that yes, I am gonna get this answer 1, 0, 0, 1. So hence they are inverses of each other. Okay. Um, so let's practice finding the inverse. Okay. So to find the inverse, what you're going to do is you're going to first write the matrix. And then when we write a line here inside the matrix, this is like um, the equal symbol for matrices. When we write a line inside the matrix, that means equal. So you're going to write the matrix A and you're going to set it equal to its inverse. And what you're going to do now, you're going to use what's called the Gauss-Jordan method from 6.2, or the some books call it the elimination method, right? But um, hopefully you know what we're talking about. So what you do is you want to make the left side look like the right side. Use you want to simplify the matrix using those steps to make the left side look like the right side. And when you do that, when you make the right side look like 1, 0, 0, 1, the other side is now your inverse. Okay, so here the inverse of matrix A is -3, 2, 1, and -1 half. Okay, all right. So how? Let's go ahead and do the steps. Okay, so first, again, to review the Gauss-Jordan elimination method. So first, um, I already have a 1 in row 1, column 1, so that one's already. But what I want is I want to have a 0 right below it. So what I'm going to do is I'm going to multiply -2 to row 1, and I'm going to add it to row 2, and that's going to give me a new row 2. Okay, so again, I'm altering row 2, so I'm not doing anything to row 1. I'm going to write it out as is, 1, 4, 1, 0. But I'm going to do this. I'm going to multiply -2 to row 1. So if I multiply -2 to row 1, -2 times a 1 is a -2, -2 times 4 is a -8, -2 times 1 is a -2, and -2 times 0 is 0. I'm going to add that to the row 1. And when I do that, you see here, I get -2 plus 2 is 0, -8 plus 6 is -2, -2 plus 0 is -2, and 0 plus 1 is 1. That goes there. So I already got one. I got two things already. I got my column, what I want. I wanted a 1 and a 0. Now let's go to the second column. Where the 4 is, I want a 0, and where the -2, I want a 1. Okay, so then let me go ahead and get my new uh, eliminate that 4. So what I'm going to do is I'm going to multiply a 2 to row 2 and add it to row 1, and that's going to be my new row 1. So I'm not altering row 2 anymore, so I'm going to write that one out. 0, -2, -2, 1, but I am going to get a new row 1. Again, I'm going to multiply a 2 to row 2, and I'm going to add it to row 1. And when I add this, you see that I eliminated my 4 there. So I have 1, 0, -3, 2. I have one more thing to do. I want to get a 1 where that -2 is at. So to do that, I'm going to multiply row 2 by a -1/2. Okay, so again, my row 1 is not getting altered, so I write that down 1, 0, -3, 2. And I'm going to multiply the -1/2 to my row 2. And when I add it, I have this. Okay, so again, the right side of the equation is my inverse. So my inverse is -3, 2, 1, -1/2. Not forget my brackets. Okay, um, so let's see here. Um, so that was to do it algebraically, but only if you need to find the inverse of 3 by 3, 4 by 3, whatever matrix, mm, you have to use it, do it algebraically. But if you ever get a matrix that's a 2 by 2, and only for a 2 by 2, you can use this formula. Okay, this only works for 2 by 2 matrices. To find the inverse, you're gonna do 1 divided by the product of the values, the elements of AD minus the elements of BC, and you're going to get your matrix. Okay? So, for instance, if we want to practice really quick using the formula, find the inverse A, again, to find the inverse, it's going to be 1 over 1 times 6, which is the AD, minus the 4 times 2, which was the BC. So this is going to give me, um, and then I'm going to multiply times my matrix here, which is, I'm going to swap the variables. The only thing that I swap is the A with a D, and then I change the sign of the negative B and the -6. Okay, so once I've done that, and I multiply by this fraction, okay, the 1 times 6 is 6, 4 times 2 is 8, 6 minus 8 is a -2. So I'm going to multiply -1/2 times this matrix. 6, -4, -2, 1. Again, this is just a scalar multiplication. So when I do this, um, -1/2 times 6 is a -3, -1/2 times a -4 is a +2, -1/2 times a -2 is a +1, and -1/2 times a 1 is a, um, oh, that there's an error there. It should be a -1/2 at that last one. Okay, so on this one, for to do our inverse, and I'm running out of time. Since it's not a 2 by 2 matrix, there is no formula to solve for this one. So I had to do the Gauss-Jordan elimination method to do this. So again, do the process to make the left side look like its identity. Since it's a 3 by 3 matrix, it has to look like 1, 0, 0, 0, 1, 0, 0, 0, 1. And when I do that process, here is my matrix. Okay. Um, so again, I'm gonna skim by really quick. For those of you who would like this work, again, it gets uploaded to our EPC YouTube channel. I want to thank you all for joining us. Today, I guess I still have 2 minutes. Does anybody have any questions? So again, you can wait for it to be recorded on the YouTube channel. But Mr. Assisi, this is his presentation, so you can email him. I'm sure you guys are already aware of his email. You can email him, and he'll send you this PowerPoint presentation to you. Okay, so again, I thank you all for joining us today. And you guys have a good weekend and good luck with your classes.
Thank you so much, Mr. Carizasis, for the wonderful presentation. We want to remind you that all of our previous recorded sessions, which are available on YouTube on the Tejano Virtual Events playlist. This session is also going to be available on that playlist later on today. Also linked is a short survey to help us improve the Tejano virtual event sessions. Please take a few minutes to fill out that survey. Before you all leave, I want to share that the Tejano virtual events flyer with the sessions that we will have next week. At 1 p.m. today, we're going to be having the nursing programs and resources, and we will be back with Happy Math Hour next week at 11 a.m., where in Math 1314, we will be covering the linear and nonlinear systems, and Math 1324, we will cover Exam 3 review. Our 1 p.m. session next week will be on Gardening Club with Mr. Isasi. And thank you all for coming in today. We hope that you all have a lovely weekend. And if you have any questions, please feel free to use the chat or your mic. We hope to see you again soon for the Happy Math Hour next week. Thank you.